So could you please tell us about who you are?
Yeah, hi, my name is Jessie Lauzon. I'm a seventh year graduate student at Stanford University, and I'm working on my PhD in aeronautics and astronautics.
And why did you choose to become an aerospace engineer?
Um, well, I always liked math and science growing up, so that's why I chose engineering. But when I went to undergrad, I went to University of Illinois at Urbana-Champaign for undergrad. Um, I didn't really know which type of engineering I wanted to study. I was also interested in chemical engineering, but there's other types like electrical, um, biology, and others. But I chose aerospace in the beginning just because I thought it was cool. Like I like airplanes and rockets and satellites are cool too. But after a couple years being in that program at Illinois, I really started to like it, and I decided to stay in aerospace engineering. Specifically, I really liked the fluid dynamics classes that I was taking.
Mhm. And why did you choose to become a PhD student? And in the future, do you prefer to work in the industry or in a university?
Um, Towards the end of undergrad, at first I had never considered graduate school or the PhD. I always thought I would graduate with the bachelor's and work in industry, but towards the end of undergrad, I really started to consider graduate school. I had good experiences in industry from my summer internships, and I really enjoyed those, but I also knew that I wasn't sure I would enjoy them long term. I felt like I would enjoy doing research more, and I really wanted to give that a try by going to graduate school. Um, and after the PhD, I think I will actually go to industry, but I'll go to industry in a more of a research scientist role. I've definitely considered staying in academia and being a professor. And the biggest pull for that is the teaching and mentoring opportunities. But in my internships, I've had really good mentors. So that shows that those opportunities still exist in industry. So that's why I'm leaning more towards going into an industry role.
Mhm. And could you talk about your research in the aerospace design lab?
Yeah, so in the Aerospace Design Lab or ADL, our research focuses on the design process of aerospace vehicles. So that could be airplanes, it could be eVTOLs, which is electric vertical takeoff and landing planes. So a lot of the new flying car startups are eVTOLs. Um, or it could be cars or rockets or engines, et cetera. Any design process, that's what we focus on. Um, and specifically, at some point in the design process, you might want to test your design um, by simulating the airflow over the object and seeing how it responds. Is it efficient? Can you change it somehow? However, those simulations can be very expensive. Expensive computationally, as in if you were to run on your laptop, it might take a week or more to run that simulation. Meanwhile, you can't really use your laptop because it's working so hard. Or uh, expensive financially because those resources cost money, and also expensive like time wise. Like if you want to test your design, you don't really want to wait a week for that. So my research is trying to predict or model the physics, and, and do so much quicker without too much error. So approximating those really expensive simulations so we can run them super quickly on a laptop.
Mhm. And you do a lot of database physics predictions. So how does predicting physics according to a given set of data work?
So there are two main ways I go about that. One is through, it's called projection-based reduced order modeling. So in fluid dynamics, we have the equations of motion, which is like, we actually, like given a vehicle, the vehicle's geometry and the air conditions, like pressure and temperature, we can model how that is going to, how the flow will react to the geometry of the vehicle. Like I said, that's very expensive, but it actually is like a known problem. So in projection-based reduced order modeling, we take those equations that we already know and we project them onto a lower subspace, which essentially means that we reduce the dimensionality so they're much quicker to simulate. So that method is very promising because we take information, the equations that we already know, and use them. And the second way is using machine learning or neural networks. And that is, it's a very popular topic right now in many industries, machine learning. And generally you have an input, which could be the vehicle geometry, and an output, which would be the flow field, like how is the airflow responding to that geometry. That is another way to do it, but I'm interested in doing physics-inspired neural networks. And in that case, we use the equations that we already know. We already know like the flow field equations, so why not use them? Why not use that information and try to make the neural network smarter? So those are two ways you can use data to predict the flow field or aerospace simulations.
And what is physics-inspired neural networks, and how is it used in aerospace engineering?
So physics-inspired neural networks, or PINs, is a subset of machine learning. Generally with machine learning, you don't always have to be predicting physics simulations. You could be predicting the stock market. Good luck with that, but you could try. And there's no equations for that. So like I said before, with physics-inspired neural networks, we want to use the fact that we have knowledge of the physics. People have been studying fluid dynamics for 100 years. So why don't we use that knowledge to our benefit, or in this case, to the neural network's benefit? So when we do that, we try to build the neural network. The neural network is very specific to the problem that you're trying to solve, but you can build it in a way where it's physics inspired, in that it tries to force physics onto the prediction that it's making. So that could be using the equations. Generally, it's some way of using the equations. It could be like forcing certain variables to be physical. For example, there's no such thing as negative pressure, so you don't want to predict a negative pressure, and stuff like that.
And could you also talk about your experience as an intern in Boeing?
Yeah, so I actually interned at Boeing 4 different times, so 4 summers. I started interning at Boeing my sophomore summer, so the summer after my sophomore year of undergrad. I moved around to different Boeing locations after that. But I really enjoyed my internships. The first one was in St. Louis. I was a flight test intern, so I was working on the F-18 program, and so I got to see the pilots take off in the F-15 fighter jet, and they would come back and say like how things went, if things went wrong, because they were test pilots. They're trying to improve the aircraft, see what we can do to make it easier to fly for pilots elsewhere, and stuff like that, or testing different configurations of the aircraft. I remember that summer, they had introduced something called a conformal fuel tank, which is an addition that goes on top of the wings close to the body of the fighter jet. And it's a way where they can increase the amount of fuel that they can carry. And something like that, since it changes the geometry of the aircraft, they need to test that to make sure that it's still stable, you know. So that was a very fun summer, getting to actually see these things in action. Was very cool. The other summers were more computational, which is something that I prefer. So I really enjoyed. It was I worked on several projects. I'll just list them. I worked on the International Space Station. I was working on a team that was making sure that the structure of the station would last another 4 years and be like, okay, we can continue this project for another 4 years. And they would keep doing that. When I was there that summer, they had just given the okay for until 2028. And that was the summer of 2014. So who knows how far they've gotten since then. And then I also worked on the Space Launch System, and I worked on that program for 2 summers. And that was more of vibration and acoustics. So it was the team's job, for example, when you launch the engines, like fire up the engines, you get a lot of noise and rattling, and you just want to make sure that the rocket will stay in one piece. You know, it's just like it's being shaken like crazy. So is it going to fall apart? And the team I was working for was the team that had to say, okay, we're good on that. And they had to do all of the modeling and testing for that. Modeling computationally, but also they tested things physically, like actual shock and vibration tests.
Mm-hmm. And what would you say has been your toughest accomplishment so far?
So I'm working on my PhD right now, and I think the toughest accomplishment will be finishing the PhD. I'm a 7th year grad student, and the first 2 years were masters. But for the past 5 years, I've been working on my PhD. Almost done, but not done yet. So once I'm done with the PhD, that will definitely be the toughest accomplishment. But for something that I have already accomplished, I think probably the PhD qualifying exam. It's a set of, it's like a final test, but for multiple subjects. And the real nerve-wracking part is that it's live with a professor. So the professor asks you a question and you're at the whiteboard answering it. So that can be very nerve-wracking. But I passed that qualifying exam, and that was definitely a big accomplishment for me.
And what is a big milestone that you're looking forward to in your research?
A big milestone. So like I said before, I'm working on 2 different types of modeling. One is a projection-based reduced order model, and I've been working on that for years. And then the second is the neural network, the physics-inspired neural network, and that's a new project for me. So I'm looking forward to getting good results with that model and then being able to compare the 2. And being able to write about the pros and cons for each.
Mm-hmm. And to high schoolers like me and to younger generations that want to become aerospace engineers, what would your advice be to be successful in this career?
Definitely work on your math skills. It's okay if like math isn't your strongest subject. If you want to be good at it, um, you can take the time and get better. There isn't. I don't really believe that there's inherent abilities like you were born to be good at math or anything. So as a high school student, you want to be on track to go to college to begin with. If you're a little bit behind in math, you can take some community college courses. Um, so I also want to say that if you're interested in being in the aerospace field, you don't need an aerospace engineering degree. You can have a different engineering degree. Like if I had decided to stay in chemical engineering, but I still really liked aerospace like as an industry, you can still work at places like Boeing or get a graduate degree and work on engines or even join the lab that I'm in, sort of thing. If you get aerospace needs a lot of expertise from different areas, is what I'm saying. So that they need chemical engineers, electrical engineers, any sort of engineering degree. And then if you're interested in space, there are some opportunities there, even with biology, astrophysics, just a lot of the math and science fields. They all work together.
Well, thank you for joining me and thank you for letting me interview you. That was great.
Thank you. Thank you for having me, and good luck on the rest of your high school career.